Welcome. Today we're going to talk about local linearization. It's something we've talked about before. We're going to be just a little more formal than we used to be. We'll talk about the concept, and then we'll do examples. So, what is the concept? Well, the concept here is, the black here is a function, and the blue is the local linearization. You may have heard of it before. It's called the tangent line. Basically, the local linearization is the tangent line. And here's our base point. So, I want to be a little more precise in my language of how to calculate it. So that's the difference now. Instead of find the tangent line, when I say find the local linearization, we'll be just a little more specific on it. If that's our base point and we do the point slope form, we have y minus the y value equals slope times x minus x value. So rewriting that, I have the local linearization right here. Local linearization is the value at the point plus the derivative at the point, which is its slope, times the quantity x minus the base point value. Basically, this is how far away times the slope. That's our start. Instead of rewriting this and turning it into like 4x plus 3, we're going to leave it as a term here and not merge the terms. That's the kind of the difference in how we're looking at it this time. Now, an interesting question. The tangent line, or local linearization, is not going to be exactly the same as the original function. How far off is it going to be? Well, that has to do with the slopes. In this particular example here, the slope of the function is not constant. It changes. So the thing that determines how far away we go is how far does the slope change? What is the change in the slope? And the change in the slope being the first derivative, what's the change in the first derivative? That's the second derivative. That will govern how far away we are from the original function. So the error, or how far we are away, is going to be bounded. We can't calculate it exactly, but we know for sure it's bounded. And how much is it bounded by? I'm going to write the formula out. 1/2 times the maximum of the second derivative, well, the absolute value of the second derivative, times the distance squared. And that's also an absolute value. So I'm going to rewrite this just so it's a little clearer. The error is going to be less than 1/2 the maximum of the absolute value of f double prime a times x minus a, absolute value squared. Now, if I'm squaring, the minus sign goes away anyway, so the absolute value here is not that important. But in the next lesson, when we talk about higher powers, that absolute value stays, and then this is important too. That too is important, it'll change also. But for now, this is the formula. Now the maximum, the maximum between, if this is our a and this is our x, whichever one we're taking, what's the biggest the second derivative is in that range? And sometimes it's a little tricky to calculate that, so we estimate. But that can tell us how far we are. If they're confused, hopefully you won't be after we do some examples. Here's the first. Find the local linearization of y equals x e to the 2x at a equals 0. Okay, how do you do it? Well, the local linearization is essentially the tangent line, but we're not going to write it like a tangent line. We're going to write it as L of x is f at our base point, which is 0, plus f prime at our base point times x minus our base value for x. Now that means we need the value of the function here, and we need the derivative here. I know what the value is. When I plug 0 in for x, I get 0. I don't know that slope yet. I'll figure it out. X minus 0 is just x. So that's going to be my linearization of the function. Now, to find that, I just need to take the derivative. What is the derivative? This is a product. So the derivative is a product rule. 1 e to the 2x plus now the derivative of e to the 2x. We've learned this. It's 2 e to the 2x. That's the chain rule times x. But what I really want is at 0. Y prime of 0 or f prime of 0, depends on how you look at it, to be 1 e to the 2 times 0 plus 2 e to the 2 times 0 all times 0 there. Whatever this is, 2 times 0 is, well, 2 times 0 is 1. I'm sorry, try that again. 2 times 0 is 0, e to the 0 is 1. But times 0, this part's 0. But e to the 2 times 0 is 1. I get 1. So this is 1. So L of x here is x. If you want to approximate this function by a line, the line is y equals x. Let's try a second example to see how linearization actually can be practical. Let's use the local linearization of y equals square root of x at a equals 25 to use it to estimate the square root of 27. Okay, we need the linearization. So again, the linearization is going to be f at our base point plus f prime at our base point times x minus our base point. So we need f at 25 and f prime at 25. The function y equals square root of x, so f of x here is square root of x. Square root of 25, then this is 5. The derivative, we have to take the derivative. What is the derivative of the square root of x? Well, square root of x is x to the 1/2 power. So the derivative is 1/2 x to the minus 1/2. Or you can rewrite it as 1 over 2 square root of x. And in this particular case, square root of x, square root of 25 is 5. 1 over 2 times 5 is 1/10. So that means L of x is going to be 5 plus 1/10 of x minus 25. I can multiply that all out and simplify. If I wanted a tangent line, I would. But for our local linearization, this is the right form. My next question was estimate square root of 27 using this. Square root of 27, you have a calculator, you can plug it in. But this allows us to estimate it without a calculator because, let's do it. L of 27 is going to be 5 plus 1/10 of 27 minus 25. Plug that in. 27 minus 25 is 2. 2/10 is 0.2. I get 5.2. I'm supposed to now compare that with the actual value. And the actual value, your calculator has a slightly better formula than a linearization. So what is the square root of 27? I get square root of 27 is 5.196, and there's more digits. Notice it's really close. So an interesting question. How close would the formula actually predict it to be? Let's do the error bound. Remember, the error bound says the error, whatever it is, has to be less than 1/2 times the max of the second derivative in absolute values times the distance you are away squared. Now, the second derivative would be the derivative of this one. Take the derivative of that, you get minus 1/4 x to the minus 3/2. Or minus 1 over 4, x to the 3/2. Might as well just use it that way. How do you use this? What is the biggest that can be? Well, an interesting thing. As x gets bigger, the bottom gets bigger. As x gets bigger, the bottom gets bigger, which means the fraction gets smaller. So if we want to know how big that possibly can be, it's going to be the biggest at the smallest possible place. And we're talking about between our starting point and our ending point. So if that's going to be biggest at the smallest is right here at a equals 25. So the max will occur when we're at 25. That's not always going to be the case. Sometimes it's very difficult to figure out the exact one. But right here, it works really well. So we get minus, well, absolute value gets rid of that. We get 1 over 4. 25 to the 3/2 is 125. So that's 1/550th. But we got a 2, we got a 4, we got 125 there. That's 1,000th. Here, 27 minus 25 is 2 squared. So this whole thing is equal to 4 over 1,000, or 0.004. This formula is going to be good to within 0.004. Look at that. Is it? I didn't write the rest of the digits here. The rest of the digits are like 1, 5 something. The actual distance away is 0.00385, which is just barely smaller than that. This error-bound formula works. The linearization is a good approximate for the original function. Until next time, this is Dr. Joe.